Well, let's go ahead and get started. It's 8 a.m., Tuesday, third lecture. So we've wrapped up the first week. First week is really pretty much review. You've seen this stuff in some form or another. Some of you may not have seen this thing of a transport theorem, but you've probably seen the cross-product-like rules, maybe not quite applied this way. So when you're doing homeworks, please be sure to use the transport theorem. These are not very complicated homeworks. It's all about practicing the principles of this stuff. And so some general guidelines I already gave you, right? Write your position vector. Then you want, you do it the easiest way possible, really the laziest. And we often introduce new frames. And in this homework in particular, you'll find from the inertial frame, we do a frame that's a one rotation about one of the axes that points out to the disk. And then from the disk, we rotate again, that's a new frame. And sometimes I show you frames, sometimes I don't show you frames. That's where you get to get creative and call them Fred and Harry and that away, whatever you want to do, to make the graders fun, life fun. But when you have that, you need angular velocities. So Brian, how many angular velocities do you have to determine?
I mean, it would depend on the problem, but probably just the reference frame that you're looking at.
Okay, let's say we have multiple frames. Let's say I have 3 frames. How many angular velocities would you need?
3.
Maybe. Is it possible you might only need 2? Yeah, depends on the problem statement, right? If you have B relative to A relative to N, you might need B relative to N as well. Depends how you formulated it. So just kind of do it. But really, if you have 3 frames, and you worked out the geometry with your right hand, hopefully what's a positive rotation, about which axis are we going, about how much are we going, and you have 2 of the 3, do you really have to go through the geometry to get the third one? What was your name again? Sorry? Varadan. How do you find the third one?
It's usually we add to...
Exactly. Angular velocities are vectors. And this would be a stark contrast to what we're starting today, which is attitude descriptions, which we often write as a set of 3-by-1 numbers, yaw, pitch, and roll. Or you'll see today the direction cosine stuff, where we have 9 numbers and we choose to arrange them in a certain way. But attitude descriptions are not vectors. You cannot just add yaw, pitch, roll plus yaw, pitch, roll to get the overall stuff. There's different math we have to do. Angular velocities, though, are vectors, which is cool. Because then, once you know how to do translation, I know my position relative to this person relative to that person, and back to me. Once you know 2, you can do the vectors and add them, subtract them, just have a good notation. So usually, if you so depending, even if you have 2 frames, it's usually like n plus 1. That's kind of what you have to find. The rest you can do through summations, subtractions, and then you can go there. Good. And then the last step is always differentiate. What you want to do is avoid as much as possible sines and cosines. Really leave things in rotating frames. It's much easier. It's way more compact. More compact means there's less chances of missing a sign and mislabeling something, dropping a distance, an I becomes a J, who knows. All right? But at some point, and in somebody's homework, you will have to do a projection. Especially if you get in 3-dimensional. The planar ones tend to be pretty simple. They all work out. But if you do 3D, let's just kind of talk through that. That we'd have. I'm just going to draw up a frame. So here's a frame. I'm going to call this B1, B2, B3, and there's a well, actually, we have modern technology, so let me use color. I have a different frame. And this is the same. And I'm going to call this one E1, E2, and E3. Now these 2 frames only differ by a single axis rotation. But let's say for some reason the math that you're doing, if you need a cross product of E1 crossed E3, if they're vectors within the same frame, as long as you specify the order, what's first, second, third, you should know. First cross second gives third, right? Third cross first gives second, but first cross third gives you minus the second, and so forth. That's all the typical cross product rules you can do. That's easy. But sometimes, especially when it's 3D, you'll come across systems where you can do all this stuff. This is all in B, this is all in the E frame, but there's this one term that ends up being, let's just make up something. I need E1 crossed with B3. Now they're not orthogonal vectors, right? They're not in the same frame, so this cross product isn't quite trivial. And we have to figure out what it is. So here, when you do it, at this step, I have to either project the E1 hat vector into B frame components, or the B3 hat vector here into E frame components, right? Because then you got everything in the E or everything in the B. Which way you go in the homework, doesn't matter. Both will give you a right answer, just a different expression of writing that same answer, right? So how do we do this? So in this homework right now, these things typically, you're always defining frames that only differ by one axis. If this is my first frame, this is my second frame, then the trick is to get the right projections. It's easier to take this out of 3D into planar. The up axis, my thumb, is the same, right? So in this case, B2 hat is equal to E3 hat. That's easy. It's the other two sets of vectors that we have to really figure out. So the trick is you want to look down the axis that you're rotating about to go from one frame to another, and then you can draw these rotations undistorted. So I'm going to do that. So my viewpoint is going to be looking down here, and then you can draw this any which way you want. Let's say I have a rotation here, that's positive theta, and then from here to here, that's positive theta. It's the same rotation angle. So if I wanted to do that, I'm going to look down, twist it to make my life a little bit easier. I'm going to say that's B3, B1, and then in this case, B2 is sticking out of the board, right? So we have B1, B2, B3, still right-handed. I'm just looking down here, taking this thing, flipping it around. That's it. Now I need the E frame, and I'll use the color again just to distinguish. So we have E1, if the angle theta is 0, E1 should be B3, and then I'm rotating positive upward, so that would be somewhere here. That would be E1. And then E2 here is in the same plane, but orthogonal. Pretend that's a straight line. And then we have E3 sticking out of the board again. All right, that makes sense? So now you've drawn this. This was all 3D. Now you can just come back to a plane, because these two axes are shared. That's easy. Now we can go either way. We can choose to write an E-frame vector in B-frame components or a B-frame vector in E-frame components. Kaylee, what do you want to do?
Let's do E to B.
Okay, so let's pick E2. And really, we have to write it in B frame. There's something B1, something B2, plus something B3, right? Oh, this should be a 2. That's hard to see. There we go. Which of these something is going to be 0?
B3.
B3?
Oh,
B2.
B2 should be 0, right? Because that's the axis that comes orthogonal to this plane, right? So this one's going to be a big 2, easy, okay? That's the easy one. Now, here's the angle theta. So essentially, what we're doing here geometrically is you're doing projections. How much is this vector projecting onto the B1 axis? And that's how far we have to go. So from here, we have to go this far in the B1 direction. All these hats are unit vectors. When you draw these things out, they all have length 1, right? And this, of course, with the projection, makes it a right-hand triangle. Very, very trivial stuff. So in this case, what is this length? How far do we have to move in the B1 direction?
Cosine theta.
Cosine theta, right? That's the cosine of it. And this would be the sine of it. Now, do you have to move in the positive B1 or negative B1 directions to go from here to here?
Positive.
Positive, right. So that's it. We throw it in. Now we do the same thing here. We do the projection of E2 onto B3. So we have to go this far, sine theta, in the B3 direction. But is it in a positive or negative B3 direction? Negative in this case. So there would be a minus in front of that. And that's it. So now if I plug this in, I would have this math would simply be cosine theta B1 minus sine theta B3 crossed with B3. What happens with B3 crossed itself? 0. We like 0. 0 is good. 0 is your friend. B1 crossed B3. What's that going to give us? Shayla? B1 crossed B3?
Or B2.
Positive or negative?
Negative.
Negative, actually. Okay, good. So minus cosine theta B2. Right? That's what this is. This becomes like that. So now we did the projection where we absolutely needed it, and everywhere else we're using rotating frames, which really keeps your life easier. In this lecture, we're going to start to get into 3D descriptions. This is going to allow us to do more general, I need components from E into some other frame, and so with the DCM, we'll see how to do this in general 3 dimensions. But for the homework 1 in chapter 1, this is typically what you need. So use it as needed. Yes, sir.
I think you flipped a few things in there.
Did I?
At the top, you've got E1 cross B3, then the bottom, you defined E2. I think that switches where you've got the cosine and sine.
There we go. No,
But
did I miss it?
It's a 2, not a 3.
Did I really screw it up?
Just put
Oh,
in
no,
2.
E3.
So much for a live example.
Okay, so I was thinking about this
B3,
in
B1,
terms of,
E1, E2. This is all correct, right? So this E2 would be correct. And then if this is E2 cross B3, that would be the answer.
So I was thinking about this in terms of the algebraic definition of the cross product, just the magnitude of each times the sine of the angle between them.
Yep.
And then use the right-hand rule to figure out which direction it's going in. So shouldn't we end up with a sine at the end of this instead of a cosine?
Be a sign if you added 90.
Here, there's a...
Theta plus pi.
It depends on how the angle's defined. You can see, because we will have an E2 cross B3, the angle's actually 90 plus theta. And you put that into a trig function, and there's all these wonderful trig identities where sine plus 9, sine of 90 plus an angle is probably the same thing as a cosine or minus a cosine. That's its relationships. Because this is we're crossing here now, and thanks for pointing out, this should have been a 2, not a 1. We changed our example live. But it's E2 crossed E3, so this angle is 90 plus theta.
I'm still looking at E1 cross B3 and thinking the angle between them is
No,
theta,
we're doing this cross this, so it's this angle.
pi over 2 plus.
Yes, and that's where that becomes, that sine can be written at, so that sine can be written as a minus cosine.
So that actually brings up another question I had, which is, looking at this, I find it much easier than kind of decomposing E into B coordinates. I find it easier just to use that definition of sine theta and then use the hand curl rule. Or
Works.
rule. There's
Works.
no downside to doing that? You can
No,
think of?
it all gives you the same answer. Different paths. Everybody has different way. Some people have different way of doing cross product rules. Some write it out into a matrix and then do all the stuff. That's how they remember it. I remember more the sequence of numbers, and So, however, there's no one right way to do this.
I just wanted to make sure there wasn't some good reason that you know about because you know where we're going.
No, if it's this simple, there's really anything that works that gets you there. And if it's more complicated 3D, that's what we're doing next. We're going to spend the next few weeks talking about different attitude descriptions and how we get this rotation matrix, and that's how you always map it back and forth. And that's where I lose simple rules. It's just I look at the math and I compose this matrix. And that's where we go. But yeah, so just different ways. Some people have trouble thinking of the geometric side and how do I get these angles in 3D. So the trick I've found over the years is this helps a lot of people. But if you see the direct definition, absolutely, go for it. There's lots of ways you can do the simple math. I just don't want anybody stumbling on this stuff and getting all wrong answers. You need to know basic trig, calculus, vector math, that kind of thing. Okay? Any questions on homework otherwise? Yes, sir.
One more thing. So when I was doing this assignment, there were a few times where I had a rotating frame so that I wanted to share an axis. So say I had an inertial frame N1, N2, N3, and then I've got a rotating frame ER, E theta, and then it shares the N3 axis but in the opposite direction.
Yes.
The direction of rotation. Is it improper to define my E frame as ER, E theta minus N3?
So let me just write this out. So the question is N1, N2, N3 defined in a classic way, right?
Yep.
And then you would have ER, E theta, it's like a planar motion, right? And then the third one, you could have E3, or you can just say N3 in here. Is that what you're saying? Absolutely.
Well,
Again,
but one more complication is that because of the right-hand rule, the direction of rotation of the E frame makes that N3 negative in the E coordinate system.
N3 can only be one way. So you want to define it as a minus this?
Yeah, because it's equivalent to
You
that.
could.
It makes the cross
I
bars a
don't
little
typically
weird.
do that because that minus sign can maybe confuse me, but if I did it E3, I would write somewhere E3 is minus N3. So if I have to flip it, I've got the mapping right there. But there's fundamentally nothing wrong with defining. You've defined 3 unit direction vectors just in a negative. It is not that, it's the opposite of that way, basically. That's what you're defining, right, to go that way. But that shares the N3, and maybe that makes your algebra, and that's how you like to solve it. Absolutely. There's lots of little nuances here, and everybody, as you go through this stuff, you should look at this and go, hey, what really works for me? How is my mind thinking? Do I like trig? Do I like the geometry? Do I like just drawing vectors? Whatever works for you, you will get there, right? Okay, any other questions right now? So I've been getting Thibault?
I have a small one. It's just after you've done all your algebra, is it okay if your answer is not all in the same reference frame? Some people
I prefer
like
that.
It. You
Really.
like it. But
Let me make that clear again. All these problem statements I'm giving you to say, find the something derivative, right? If you're taking an A-frame derivative, it doesn't mean you have to map everything into A-frame. If you're taking an N-frame derivative, it doesn't have to be mapped into the N-frame. I can take the derivative of this pen relative to my shoulder, right? I take the derivative of this vector as seen by the N-frame and express it all using these rotating frames. In fact, it makes it much easier. It's much more compact. That's where it's good to stop, especially in an exam. If you continue on for 3 pages doing a bunch of sines and cosines and projections, I'm like, well, that's a lot of work. But I bet somewhere you have a whole paragraph written why you're running out of time and this is impossible to do. And I'm not going to shed any tears. I'm sorry. You should know what you're doing. You know, I'm just asking for the answer. It can be written in vectorial form. It doesn't have to be orthogonal base vectors. We can mix vectors. It really makes our life easier when we get through this stuff. So this is kind of the practice round, because we'll be using this throughout. No, if I needed you to express the answer in that, I would say, find the inertial derivative and express the answer in C-frame components. Now, it doesn't mean up front, step 1, put it in the C-frame and then differentiate. You can still do whatever's easiest. It's just the very answer. Once you get it, go, that's in the C-frame, this is in the B. Okay, I'm going to map that now into the C. That's when you do it, at the very last step. So still solve it, whatever's easiest. But in none of the homeworks do I actually ask you to express the vectors in a particular frame. So that leaves a lot of leeway in how this could be solved. And some frames you can come up with your own names. So Don will have to adjust for that in grading. Obviously, it won't just be one answer that fits everything. Well, good. So no, I'm getting a lot of good questions. I appreciate you guys jumping on homework 1, trying to get down with vectors, notations, make sure these things are clear, because if something isn't, this is every lecture we can have a little, okay, any questions about this? And if you're confused, probably 6 other people are confused, you know, please do speak up and say, this is where I'm getting stuck. Let's fix that, let's move on. The rest of the lecture will make that much more sense. If you're distance students or on-campus students who just can't make this lecture, and you listen to the lecture and you have a question, wait a minute, you know, that thing about that angle, I didn't quite understand. Could you explain that again? Let me know before the next lecture, because then in the next review, when I'm going over this material again, I can just incorporate those questions typically, and that's worked out pretty well. Okay? If it's something very particular, just email me, you know, or the TA, Don, either of us, and we'll try to respond right as soon as we can. Good. Okay, that's it for review. So we just basically finished chapter 1 pretty quickly. You're going through some examples, hopefully just warm up, get everybody in the same notation. Shouldn't be too exciting yet. Chapter 2, I would say skim through that. You will have some brief homework problems from chapter 2. It's basic dynamics. We're going to jump later on directly to the rigid body version of that. But if you haven't seen the stuff in chapter 2, F equals ma, for a particle, for a system, for a continuum, you might want to glance through that and read through that as well. So look at that as your reading assignment. What we're doing now is we're jumping to chapter 3. So the next topic, this is kind of a big 1/3 of the chunk of the class, is rigid body kinematics. So I need a rigid body. Here's some little object. It's all rigid. I can throw it around. Doesn't change shape. Doesn't deform. At least if I don't throw it too hard. So David, what does kinematics mean? Yes.
Daniel,
darn. B, I was close. I should know. Thank you.
it's the motion. It's the study of motion of whatever. Just the motion through space.
So if I'm throwing it up, are you studying how gravity affects and makes this thing fly?
No, just I'm confused now. Not sure anymore.
It's all these subtleties. You say the study of motion, which is true, but that's a really big umbrella, right? What is the specific that we're doing in kinematics?
No external forces.
Well, yeah, no forces, no torques. So what are we looking at? We can cut away everything we're not looking at. What remains? Andrew, I asked you this last time. You gave me a very large question.
So it's the description of motion?
That's really the key. It is the description of motion. If you say study of motion, that can include a description, but it also can include prediction of where you're going to be 5 minutes from now, looking at gravity, forces, all this stuff, right? So kinematics is purely about how do I describe my position? If we talk translation first, right? That's often easier for people to kind of visualize. I know, this is my point of P of interest. Here's my coordinate frame down to the floor. That's my position. Now, what type of coordinates could you use to define that? Sorry, what was your name again?
Maurice.
Maurice, thank you.
What kind of coordinates?
Yes, just a regular position.
Sure, you could use Cartesian coordinates.
What else?
Rotational, cylindrical, Maurice's fancy pants coordinates.
Fancy pants coordinates, always popular. Yeah, absolutely. Yeah, lots of them, right? I bet there's combinations, there's infinitesimal combinations, so there's infinity of coordinates. There's lots and lots of ways. But people love Cartesian at the beginning because that's what they're used to, right? But then as you get in more complicated systems, you've got a spacecraft crawling on a Ceres, which is a pretty spherical-looking asteroid. It's huge, right? That's the one that had all the white dots recently that people have. So if this is a sphere and you use Cartesian, well, now you're going to have these constraints that x, y, and z all squared have to sum up to the radius of this asteroid, right? And that's a pain to keep track of. Versus if you now switch to spherical, yeah, spherical is a little bit more complicated. Lots of sines and cosines and a little bit different coordinates and relationships. But now all of a sudden, that being on the surface just means your radius has to be constant, right? And now you're acting on it. Life becomes much easier, actually. The control of this becomes much easier. And the same thing happens in attitude. And that's what we're covering right now. But instead of translation, which are vectors, attitude is not a vector. That's one of those easy, quick answer questions you might have in an exam. Is attitude a vector? And if you say yes, I'm just going to blast you. So, no pressure. So rigid body kinematics, it's the description of the orientations. How do we get there? And we're going to go through a whole series of these. Today, we're going to cover the direction cosine matrix. This is sometimes also called the transformation matrix or the rotation matrix. I typically call it DCM for short. You know, in space, everything has to have acronyms, otherwise it's not respected. So this is called DCM. And that's one of them. Euler angle sets, this is hopefully something you've seen. So we're going to breeze through these pretty quickly. But the key elements is always, for every single set, how do I add them? How are they defined? Where are they singular? How do I subtract them if I have relative orientations? And in particular, how do I map back and forth to the DCM? You will find reasons why shortly. There's other things called principal rotation parameters, Euler parameters, classical Rodriguez parameters, modified Rodriguez parameters. We'll even talk about stereographic orientation parameters. There's a whole series, and there's lots more that can be defined. There's still papers being published to this day on different kind of attitude descriptions and how we go back and forth. And so as we go through them, at the beginning it's a little bit more detailed. We're covering a lot of what exactly does this stuff mean, how do these things relate, how do you get to them. As we get to the lower part of these coordinates, we'll start to accelerate a little bit because it's kind of the same concepts over and over, but now we're using this definition, then this definition, and what I expect for you to have by the end of this whole thing is a really intimate understanding of how to describe orientations. And if somebody gives you a coordinate set you've never seen before, you should not flinch and go, you know what, I just have to find, this is what I have to find, and now I'm ready to go. And there's some clear ways to deal with it. This is a topic that's very, very popular with people, especially once they leave this class and university and go work at JPL or Lockheed or who knows where. Because 3D orientations to this day still confuses a lot. And how do you define it? What does it mean here? Or the notation isn't always very clear. So we're going to try to do this in a very nice, clean, easy to use, rigorous way. That's one of them. So many of you will have seen sets of these, parts of them, but none of you probably have seen all of this stuff. Especially when we get to some of these things, there will be lots of head scratching. That's fun, right? You're here to expand your envelope. So, attitude coordinate sets. One of the definitions is basically, if we're talking about the orientation of a rigid body, which here I'm showing through a spacecraft, and I've attached this B frame, this is a body fixed frame. If you're talking mathematically about the evolution of the orientation of this frame, or you're talking about the evolution of the orientation of this body, they're equivalent, right? Because B is a body fixed one. So if you know this frame has pitched up 90 degrees, the body must have pitched up 90 degrees. Now, how many ways can you attach a frame to a body? Sorry, what was your name? Yes.
Spencer?
Spencer, thank you.
As many as you want.
Yeah, as an infinity, right? We typically line them up with symmetry. If you're an airplane, there's the roll axis, the pitch, the yaw, and you will see the different definitions for this stuff, and that's fine. But there's really an infinity of ways, because even if you look at the space station, there might be a flight set of axes. If you're on a docking port, there's maybe a docking port axis where you really worry about all the orientations relative to the docking port. If you're a star tracker, there's probably a frame aligned with a star tracker. If you're an IMU, there's very likely there is a frame aligned with the IMU. So even on a single rigid body, in actual flight software, you might have 6, 8, 10 different frames defined, you know? Now, if it's rigid, all these orientations are fixed relative to each other. So once I know one, this is my primary frame, and the star tracker is rolled 90 degrees down, that's where it's pointing, well, no matter what the body does, I know it's plus a 90-degree rotation, and then where does that go, right? And I say plus, not in a sense of adding vectors. You will see the math we have to do to add rotations and subtract rotations. So good. So in this section, you won't see me draw a lot of spacecraft. I'm not very good at that. I'm reasonable, actually. I shouldn't have been memo myself. But the frames, you just see me always draw frames. That's it. That represents whatever rigid body we have going. There's an infinite number of these. Just as with translation we're talking about, there's lots of different combinations. I mean, there literally is infinite numbers. There's whole families I've actually published on where there's parameters that you can infinitesimally vary, and I can create parameters for you that will go singular at any desired orientation. Anybody know an attitude set that goes singular at some point? You guys are way too shy.
Euler angles.
Thank you. You took 3200. You better know that, all right? Euler angles. So Kaylee, tell me a bit which one, let's say a 3-2-1 yaw pitch roll, right? The classic yaw pitch roll. Which angle goes singular?
It's pitch, 90 degrees. 90
degrees, right? So at 90 degrees, there's a mathematical issue that we have to deal with. Sometimes this issue is just a 0 over 0. There's an ambiguity. There's an infinity of ways these coordinates could be defined at this orientation. That's one way the singularities can manifest. The other way is your coordinates literally blow up to infinity. They just become infinitely large at that set. And we'll see both sets that do this kind of stuff. If they go off to infinity, that's actually nice from a control perspective. Because if you're feeding back on attitude, you do a simple linear gain, you know, minus k times your attitude error. And if you want to make sure your solar panels haven't rotated more than 90 degrees, if you had a set of attitude coordinates whose values go to infinity at 90 degrees, you can become infinitely aggressive to restore your attitude back at the sun, right? Close to the sun, you're kind of weaker, but then as you go out, it's like a cubic or a highly nonlinear spring, you know? And I can design coordinates for you that will go to infinity at any angle or about any particular axis. That's kind of the latter part of the stuff. This is where maybe some head scratching comes in. Wait a minute, how do we do this? But it's really slick and cool. And it's plain fun. Nothing wrong with having fun. So a good choice of coordinates. We're talking about moving on an asteroid, right? If you're moving on a spherical balloon, a spherical shape, and all you're doing is using Cartesian coordinates, you deserve what you get, to be simple. All right, there's much better coordinates that will make your life so much easier. You just have to put a little effort into the kinematics. How do I want to describe my motion? And this is where laziness is good. So you want to make this as simple there as possible, but you have to understand often the simplicity comes out of dealing with rotating systems and rotating frames, which you're now practicing with the transport theorem. Once you lick that part, you're ready to go. And this will be much, much easier. A bad choice, as we said, can really have a lot of issues. It can make your life more complicated in the control. It can make your life more complicated in your dynamic stability analysis. But it can also lead to singularities. If we would use, as Kaylee was saying, yaw pitch roll for general rotations, you know, nothing says a fighter jet can't pitch up 90 degrees. The F-16 has more thrust than weight. It takes off and goes off like a rocket. Doesn't even need wings, really. Except for landing, detail. But there's parachutes, you know, you're good. So if you're going off and doing that, the plane can physically pitch up. You've chosen a description that happens to go singular. But physically, nothing prevents the plane from going up. Why did you pick coordinates that actually would prevent the control from allowing the pilot to do such a maneuver, you know? So same thing happens in spacecraft. You see a lot of people that have historically used yaw pitch roll. There was a big government space sponsor, not to be named and embarrassed, but you know who I mean, starts with N, who always used to require 20 years ago, all the controls, everything has to be done, not the controls, but everything, all the analysis, everything has to be done in Euler angles because they're easy to understand. And I'll show you why that's not exactly the case, especially not for large rotations. Because now you're introducing singularities and you control your estimation, all is handicapped by your choice of kinematics. And there's other sets that are much more applicable for large rotations. Every single set of coordinates we use has an application. And you will find cases where, wow, I'm glad I know Euler angles. I'm glad I know DCMs. I'm glad I know quaternions, you know. But you need to be familiar with, this is like your toolbox, right? You don't just want one wrench, one size in there. You want a whole set of tools to understand whatever the problem is, I have the right tool that's going to do the job effectively. That's essentially what we're learning in this section. And this is a good chunk of the class. Everything kind of builds on this. Fundamental differences in orientations. So back to the translation example. If this is my position, and then you have something else moving relative to it. So we've got two objects. They can be very close, they can be very far. How far apart could they be? Wait a minute. Is it Kevin?
Yeah.
Yes. How far apart can you be translationally? And we're dealing with Euclidean space. We're not going into Einsteins and curvatures and stuff.
I mean, you can be any distance.
Yeah. Any means infinite, right? So your tracking errors can actually become infinitely large. So for engineers, for all practical purpose, that's good. Well, but it also means if you're doing feedback control, you're doing gain study, if you do a simple feedback, k times tracking error, and tracking error goes to infinity as you go far, far away, you're hitting it with a huge control effort, which is very likely going to saturate it, and now maybe your stability analysis breaks down, or other issues might come in. And we'll see saturation when we get to the control side of the class. Attitudes, though, are a very different beast. So with attitudes, if you're looking at this, just do 1D attitude, you know? If this is where I'm supposed to be pointing, but for some reason I'm not paying attention, I'm talking to this wall, my attitude error is about 90 degrees. If I'm really tired and I'm talking like this all lecture long, you know, you probably should throw tomatoes at me, but you know, my attitude error is 180 degrees. If I keep on wandering and start talking this way, my attitude error is 270 degrees. Is 270 worse than 180? Sorry, what was your name? Rick.
Brett, sorry.
Brett, sorry.
What do you mean by worse?
You know, I'm making the numbers bigger. This was 0. This was good. 90, 180, 270. It sounds like 270 is worse than 180.
Better.
It's actually better, right? So the fundamental thing that's built into attitudes is there's a finite set. Mathematically, it's called the SO3 group. So if you read papers on attitude stuff and see SO with a 3, it's a mathematical description of this group. That's what we belong to now in the attitude coordinates. They're not part of a vector group, where you can do vector addition, subtractions, and so forth. SO3, so there's a finite limit. You can rotate, make it bad, get so, it's as bad as it gets, and that's 180 degrees. You would never have infinite angle, because at some point, you're going to revolve again about the orientation you want to have. This is really important in control. You will see this when we try to do detumble control. Some descriptions automatically take advantage of this. Others, not so much, right? And so depending on what you're doing, they have different benefits and drawbacks. But this is very practical. So I can tell you, teaching skydiving, right? We're hanging out outside the plane. There's a high wing plane. We had a Cessna 182, little strut. The student stands out there. This is an AFF program, accelerated free fall. One jump master holding on the left, one jump master holding on the right. And then we have supposed to leave together. The student's supposed to up, down, and step gently off into the wind, arch, you know, put hips forward, arms back, legs back, so you kind of fly like a butterfly. That's the theory. The reality, a lot of profanity, you know, pushing, shoving, kicking, and off we go. And there's one video I got in California that was really cool. I did this jump with the jump master. We went, and the student really shoved off hard. And we're both trying to stabilize it. But there was so much momentum put into the system. You know, we're just basically going upside down. And I look over, and we're kind of smiling at each other, going, oh, what the hell. And we just basically complete the tumble, flatten out, fly on the rest. The student had no clue. This is their first jump, you know. You get blackouts and everything. But that's basically it, you know. Instead of trying to unwind it and fight it all the way, at some point you're going, hey, from an attitude perspective, it's easier to just flip it all the way around and recover here again. If you're unconstrained, you know, if you're a mechanical system that has wires attached and you can only rotate so far before you rip out wires, well, then it really matters. You really want to make sure you don't just cut everything loose. But in space, we're typically tumbling freely. There's no constraints. So again, these tumbling things, you will see something throughout the class we keep talking about. Why do we describe one way versus another? Which one helps us in the control? Which helps us in the dynamic prediction? So attitude errors can only get up to 180 degrees. For truths, you need a minimum of 3 coordinates. We live in a 3-dimensional world. Right? So your position has 3 things, but also your attitude has 3 degrees of freedom. So your orientation needs a minimum of 3 coordinates to define any general attitude. Okay, that's easy. But a minimal set of 3 coordinates will have at least one geometric orientation where the description becomes singular. And as we just mentioned, singular might mean ambiguities. You got 0 over 0 in the math because this angle could be an infinity of angles. And you will see different cases of that. Or it means your coordinates literally go off to infinity. You got something finite over 0 at that orientation, and now, big numbers. So both ways you have issues. And those are called singularities. So at or near the singularity, the kinematic differential equations are also singular. We're going to develop this equation. This is basically the equation that relates this omega that we've developed, the angular velocity vector omega. That's what we measure in a rate gyro. That's what we use to actually derive our equations of motion in the future. But when we integrate and have yaw angle, pitch angle, or quaternion rates, or DCM rates, we have attitude coordinate rates that has to relate to these omega. That's our differential kinematic equation. We're going to see it over and over and over and over again. But that's the equation that would go 0 over 0, or something over 0, which makes this whole thing blow up. Now, these singularities, or these 0 over 0 issues, can be avoided by moving to more than 3 coordinates. So you need 3 just to do generally tumbling objects, and there's coordinate sets that can avoid singularities at the cost of additional coordinates. Anybody here heard of a coordinate set that's non-singular? Go ahead.
Quaternions?
Quaternions. Euler parameters is one of them. And there's different sets we'll see, actually. There's several sets that come up here that will be non-singular. But it's always with 4 or more. So let me invert that. Several of you have heard this before. If I have a set with 4 coordinates, am I guaranteed it's non-singular?
Lewis?
Yeah.
No, because you could just have a redundant set that doesn't add any.
So just having 4 coordinates doesn't guarantee that you're non-singular, but it allows the option of having a smart set, and there's lots of different sets. And chapter 3 we'll be going through most of them, not quite all of them, but there's a bunch of them that do that. So we have to always go to more than 4. Everything builds on this DCM, this direction cosine matrix. Now we've done with the review of just what this kinematics is about. Let's talk specifics here. So we got a good 35 minutes. Good. The direction cosine matrix. Again, lots of different names. When I say this is the mother of all parameterization, I really mean it, because you will find every single definition that we have of attitude coordinates. If you publish on this, somewhere the reviewers, the editors are going to look for, great, I love these coordinates, but how do they relate to DCMs? Because DCMs is going to be the way that we do fundamental addition rotations, coordinate transformations. Like you can translate between Cartesian and spherical coordinates, there's math for that. This DCM is the fundamental way that we'll be translating between sets of coordinates as well. So this is one we really want to understand, and we use it a lot. It's a very, very important one. So hopefully, has anybody here never seen a rotation matrix, DCM, transformation matrix, something like that? You should have used this at some point, even as a physics major probably, or a double E. It's not just an arrow. So let's go through this. Again, the fundamentals is more review at this point, but I'm trying to get everything in the same notation. The first, we have 2 frames. We have the B frame here in blue, and we have the N frame in black. And the definitions of angles I'll get to in a moment here. The first thing I want to define is this concept called a vectrix. It's a convenient way to do linear algebra with vectors. So all a vectrix is it's a matrix of vectors. And if I do a quick example, if I have to do math, if I have to somehow evaluate 3 times B1 plus 2 times B2 minus 5 times B3, I can actually write this as 3, 2, minus 5 times this vectrix of B1, B2, B3. Right? You just do your usual, it's going to be this times this, this times this, this times this. And the math implicitly involves scalars times vectors, and that's fine. So the answer is a vector. But the vectrix is just a matrix representation of typically sets of base vectors. This allows us to group the linear algebra in very convenient forms. Okay? So nothing too scary or unusual there. Good, so that's the vectrix, and we have here the n vectrix, which formed by the base vectors n1, 2, 3, and the b vectrix, which is b1, 2, 3. To denote the difference, I'm using a curly bracket around the b hat. It just means this. If you see this, you know this is a 3x1 matrix of some of the b base vectors. That's it. Now, let's look at this stuff. We did this projection earlier, right, where we talked about in homework 1, you're going to have to do projections of E frames onto B frames at some point if you're doing three-dimensional rotations, and you figure out which sine and cosines to include and so forth. This is really developing to a much more general way. If you have to write B1, this vector here, in n-frame components, you really have, well, B1 is something along n1, something along n2, and something along n3. And these somethings are the projections. These are all unit vectors. So how far do you have to move along this way? It's the dot product between B1 and n1, which gives you magnitude 1 times magnitude 1 times the cosine, if you're thinking of those classic Laws definitions, of the angle between the two. So this element that you have to go, this is simply cosine alpha 1, 1. 1, 1 means it's between B1 and N1. 1, 2 means it's between B1 and N2, and 1, 3 is it's between B1 and N3. So with those three projection angles, essentially, or here direction, they're cosines, that's where the name comes from, direction cosine angles, or direction cosine matrix in the end. You can write B1 in terms of the other for a general rotation, not just when they differ by one axis. And then for 2 and 3, it's really the same process, but instead of having 1, 1, 1, 2, you have 2, 1, 2, 2, and or 3, 1, 3, 2, and so forth, right? Because you're doing the first, second, or third body vector. So that's an easy way to just do a simple projection. Now that's three equations, three vector equations. You have to solve and do things with them. And as you know, if you have to deal with multiple equations, the way to go is really linear algebra. That's a great mathematical tool to kind of manage all this stuff and solve systems of equations. So let's put this in linear algebra form. We have here on the left-hand side, I'm going to make this the b vectrix. And on the right-hand side, I'm going to have the n vectrix. And then in between, we have this 3 by 3 matrix of direction cosines. I've just plucked it all into linear algebra form. Hopefully trivial at this point, just to go from one side to another. And I'm going to call this matrix the C matrix. Right now I'm just using one letter. Later on I'll go to a two-letter notation that you'll see. If you're dealing with lots of frames, that two-letter thing is really, really handy. But we can do this. So good. This is what relates the N frame to the B frame in a general way. So therefore, this describes the orientation, and as Daniel's pointing out earlier, it's the description of attitude motion. That's what kinematics is. So therefore, these cosines are actually attitude coordinates. The question is now, how many attitude coordinates does the DCM have? Robert, what do you think? Three coordinates.
9.
Why? It's not a tricky question. You're probably thinking too far. How many cosine values do we have here? 3 plus 3? 9. Okay, say it with authority. Great, 9. How many do we need, Robert, to describe a three-dimensional orientation?
3.
3, right. So we needed 3. I'm showing you this DCM as a fundable thing, and holy crap, we went way too far. We got 9. How do we end up with 9? Well, this is the basic definition. The DCM is a highly overparameterized set of attitude coordinates. So if the DCM has 9, Thibaut, does this mean we all of a sudden now have a 9 degree of freedom system?
No, some of the angles can be rewritten as the sum of others, etc.
Right. In essence, there has to be constraints. This kinematic description has constraints. And if you have 9 coordinates and it's a 3-degree freedom problem, how many constraints? Sorry, give me your name again.
Andre.
Andre, sorry, I should know. How many constraints must we have, Andre? So what happens with the other 3 equations? If you have 9 coordinates, 3 degrees of freedom.
You need 6.
6, right? So you have 9 coordinates minus degrees of freedom, that's how much you've left. If you have 3 coordinates minus 3 degrees of freedom, means you have 0 extra stuff. That's it. It's a minimal description. If you have 4 coordinates minus 3, there must be 1 constraint. Here, there must be the equivalency of 6 constraints. And there's lots of ways these constraints manifest. What can you tell me about this DCM? If we look at it now, if somebody, let's just switch over. You've seen the definition. You've all seen this before. Nobody raised their hand, so everybody's fair game now, right? That'll wake you up. If I give you a DCM, 1, 1, 1, 0, 0, 0, 0, 0, 0, could this possibly be a correct DCM? Yeah, why, Chuck?
2 frames could be...
Don't tell me what it means, but just looking at it up front, your gut feeling says this could be right. Some of you may recognize identity. Yeah, I remember that from somewhere. That actually means the 0 rotation. Good, you might recognize it. Let me put this elsewhere. If we have 0, 1, 1, 0, 0, 0, 0, 1, 1, a bunch of zeros and ones I've thrown in there. Brian, could this be a proper DCM?
Excuse me, I don't think so.
Okay, you have 50-50 chance, so can you elaborate?
Because that would mean that one coordinate is aligned to 2 axes.
Right, so if B1 is N1 plus N3, what is the length of B1?
1.
It should be 1.
Right.
Is it 1 in this case?
No.
What is it? You're close. Not there yet.
There's 2.
You got N1 in one direction, N3 in another direction, orthogonal. You add the 2. What's that length of this triangle? There you go. Okay? It's all going to be more, right? So really, as you can see, because every row represents the B1, B2, B3 vector components, these components better add up to 1. You do 1 square, 2 square, 3 square, right? They have to have unit length. So if you're doing some problem and you're doing something like that, and you end up with a matrix that says, 3, 5, 7, right away go, stop right there. You're not on a good path, right? There's no way this could be a DCM. Doesn't make sense. So every row has to add up. Every element has to be a cosine of an angle. And cosine functions gives us what range of numbers? No, not -1 to 1, right? So you could have a -1, you could have this, but you can't have more than -1, you can have less than, you can't have less than -1, you can't have more than +1, and this kind of stuff. So immediately you can see there's lots of geometric constraints on what these coordinates can be, and in the end they're all equivalent to being 6 degrees or 6 constraints that have to be applied. So let's go back to the definitions. We'll discover more and more relationships and what this stuff means. Again, you've seen DCMs. So the definition, the ijth element of this DCM matrix is simply the cosine of the angle between the ith and jth base vector of each of the respective frames, right? And this is B and N. Those are placeholders like the transport theorem. This could be Q and T, S and R, whichever 2 frames you're doing, the attitude of this frame relative to that frame. So it's a dot product of 2 unit vectors, which just gives you that cosine. So good. So we've got that. This basically maps, you can see here, we're going from n-frame components and computing now what the equivalent B1, 2, and 3 are. If you want to do the reverse, you could have just taken N1 and gotten B1, 2, 3 components, N2 and gotten, I can flip B and N, really. If you do that, it's the same angles, it's the same 2 frames, but all of a sudden, instead of 1, 1, 1, 2, 1, 3, we end up with 1, 1, 2, 1, 3, 1. The indices become flipped if you have to do the projection of N onto the B frames. But otherwise, it's the same matrix. So the matrix that maps the B vectrix into the N vectrix is really C transpose. It's just a transpose of the original matrix. But mapping-wise, here we went from n to b, and then here we go from b to n. What type of mathematical operator are we doing here? If one takes you from n to b, and now you want to go from b back to n, what do we have to do? Inverse. You could have just taken the matrix inverse up here, brought it over, right? That's where linear algebra really shines. You know how to do that. It's a bunch of numbers. Give it to MATLAB. You just made MATLAB's day. It loves doing this stuff. And here's an inverse. Bring it over, and now you do it. But the beauty is, we can see for the DCM, it turns out the inverse is nothing but the transpose. What do we call such a matrix when the inverse is equal to the transpose?
Orthogonal?
Orthogonal. Or also, in this case, if you want to be very specific, orthonormal. But we'll typically use orthogonal. In all the attitude papers, they just talk about orthogonal. And that's good. If you took a linear math and applied math, they probably talk orthonormal because it's on a normal length-based vector. So really, that's what we just discussed. The matrix inverse in this case is just a transpose. That means anywhere you see a problem, not just in attitude dynamics, and you come across something in structural modeling and other things, and here's a system mass matrix and it's orthogonal, that is good news. Sometimes people shy away from this and oh, that makes it sound complicated. No, orthogonal is really good news. That makes your algebra much easier. If you have to analytically solve now for these inverses and do it, anything more than a 2x2 quickly takes up pages and pages of algebra. Just go in something like MATLAB or Mathematica and plug in a 4x4 matrix and ask it to invert it analytically. It'll do it. Then it'll be, don't print it out, you'll kill a lot of trees, but it'll take lots and lots of space to do it. So if you can just do a transpose, that is fantastic. Okay? Now, let me talk about the two-letter notation that I use, because you will see this often when we solve problems. The C matrix is a classic definition. You see it in lots of different literature. But also, if you have multiple frames, things get a little bit more complicated. Then you really want to track, this is the attitude of B relative to A, then A relative to Q, and Q relative to R. And you don't want the C for everything, because it gets very confusing. So we'll tend to use what we just defined as C is really what I have as a Bn matrix. Some people write this as T, the transformation matrix, with B and N, or N and B flipped. There's a whole series of different notations. So if you have a paper you're not familiar with and have DCMs in there, first thing you should do is look up and really understand how are they defining this mapping. Is it from one to the other or the inverse? Because it's not universal. In astrodynamics, we do everything in the body frame. Our equations of motion are simplest in the body frame. Our sensing happens in the body frame. And so everything is mapped into the body frame. If you go to computer science and robotics literature, they do a lot of the same stuff. Computer graphics, how do you map all these things and these pixels and vertices and over and do all this stuff? But they map everything by default into the inertial frame. All the robotic stuff is typically written in the respect to an inertial frame. And everything's, the complex kinematics is all mapped back to that. So all their definitions are exactly flipped from what ours are. I didn't invent it. I'm only the messenger. So just pay attention, And even sometimes across fields, I found, I was working at Sandia, there were some things people call them Rodriguez parameters, and you solve, define Rodriguez parameters. But it turns out in that field, Rodriguez parameters meant what was to me, not Rodriguez parameters, but principal rotation vector. That's about an afternoon wasted until I finally tracked down, why does this math not work? And they were talking about very different coordinates. So it's just, lots of fields have contributed to attitude kinematics, and so there's just a whole plethora of different definitions and ways to go. So Bn, why is this handy? This is what we had for the B vectrix is equal to Bn n vectrix. With this two-letter notation, somewhere you're denoting this rotation matrix goes from this frame to this frame. And in the attitude, you will see we always tend to go from the right-hand side to the left. We start from the right, this is where we begin, then we start superimposing multiple rotations, and at the end, we end up on the left. Just the way it goes, so from right to left. That's good. If I want to invert this matrix, how would I denote that with this two-letter notation? NB, right? That's it. So you can just say NB ends up being Bn transpose. It's very simple. And so you will see this. For right now, if I'm just doing one frame, sometimes I just write C. It's easier. So we'll see. Okay, so good. So this orthogonality inverse, that's really important. If you looked at the DCM examples we did, we said every row of this one had to be a unit length. But because if you invert it, you're mapping B frame stuff onto N frame also N1, 2, 3 are unit vectors. Therefore, every column of your DCM has to have unit length. So there's other issues that come in now with the DCM. Let's talk about that then. Since this maps onto there, one onto the other, could I have 1, 0, 0, 0, 0, 1, 0, 1, 0? Would that be a proper DCM? It maps one frame to another. Why not? You're shaking your head. Sorry, what was your name?
My name's Ansel.
Ansel, thank you.
I think it would be left-handed.
Good. So the zeros and ones make sense. Nothing would violate the cosine requirement, right? The lengths, this has unit length, unit length, unit length, unit length, unit length, unit length. That's all cool. But if this maps n to b, b1, 2, 3 had to be right-handed. And you can see here, if this is 1, this is 2, 1 crossed B1 crossed B2 doesn't give me B3, it gives you minus B3 in this case. So this is where somebody used their left hand to construct a coordinate frame, and you end up. This is also an orthogonal matrix. It satisfies all the conditions of orthogonality, but it's a left-handed system. And so there's some mathematical checks we can do to quickly identify, is this DCM left-handed or right-handed? And we'll check for that. These orthogonal matrices also come up when you do projections. So there's some mathematical operators for projections, mirroring, that kind of stuff. And with mirroring in particularly, you could end up with a left-handed, type thing. You will see that in a moment. So here too. So this I can look at it and go, well, that's not done for, it's not for an attitude description with a right-handed coordinate frame. That was the issue. So very good. Okay. So you've seen this, we're trying to creep through it, put this all together. So how do we identify some properties of this? Here, let's look at the determinant of the DCM. And the trick on how to evaluate this is we don't look at the determinant of C directly, but I'm going to look at C times C transpose. Since C transpose is the inverse, I'm really doing C times its inverse, which has to be identity, which is trivial. The determinant of identity, everybody here should be able to do in their sleep. Without lots of let me think. This should be basically 1, right? That's it. So we know the right-hand side. Let's expand the left-hand side. Since C is a square matrix, there's linear algebra properties. A determinant of A times B is the same thing as a determinant of A times the determinant of B, which we can use here. So good, we got that, broken it up. And the determinant of C and its inverse, actually doing an inverse of a matrix doesn't change its determinant value. So that's cool. So we can really group these. It's nothing but the determinant of C squared has to be equal to 1. So that's a fundamental property that we can derive right here. And so that means the determinant of C has to be the square root of 1, which is plus minus 1. So up to here, this is just dealing with an orthogonal matrix. The only assumption we made was that C is orthogonal and satisfies that C transpose is equal to I. That's it. We made no statement about it being a representation of a right-handed coordinate frame relative to each other, right? Orthogonal matrices appear in lots of places, not just in attitude description. So a general orthogonal matrix must have a determinant plus minus 1. If it has a determinant of 2, it's not an orthogonal matrix. Somehow you're scaling the vectors bigger than they should be. Right? But it's plus minus 1. If it's doing a mirroring, it ends up being actually a minus 1 operation. Or if it's a left-handed system, it'll give you a minus 1. So for us, dealing with attitude descriptions, we're expecting a right-handed coordinate frame mapped onto a right-handed coordinate frame to stay just in sync. And that means we have to have a plus 1 determinant. And that is called a proper rotation or a proper orthogonal matrix. If you see the word proper in front of orthogonal, that's what we're talking about. Just think right-handed. But mathematically, it means the determinant is plus 1. So if you just take any orthogonal-looking matrix and do a determinant operation in MATLAB, and it gives you plus 1 on the 3 by 3, that's a representation of a right-handed system. That would work. Any questions on this? Proper orthogonal. It's a simple derivation. Yes, this is something you should be able to do in an exam. It's a blank sheet of paper. There's some simple rules to get here. This is the logic, and this is where we end up. Coordinate transformation. This is probably the most practical use of DCMs. We talked in homework 1, we're trying to stay away from coordinate transformations, do everything in rotating frames, but at some point you just can't help it. You need to do a vector here, crossed with this skewed vector here. How does that work out? And if we have nice problems, like in chapter 1, where they only differ by one axis, there's easy ways to do it. But sometimes it's a full-on 3D geometry. How do I map one to another? That's where we use this. So there's different ways to write it. I'll give you this note, but I'm going to go back to an example in a moment. It might be just an alternate way. You've got this slide. I'm showing you an alternate way how to get it. But the V vector can be written as, something B1, something B2, something B3, or the V vector can also be written as something times n1, n2, n3, right? There's an infinity ways to break this vector into 3 sets of orthogonal components. So at every one of those cases, we can use the vectrix forms where the components are written as a 1/3, or a 3/1 in this case, transposed with the vectrix, and you can do that. And these vectors have to be the same representation, so you can put this around. But in essence, what this quickly proves to you, and I'm sure you've seen this before. So if you go through this math, if this is the n-frame vectrix components, the n vectrix is nothing but C transpose to B vectrix, and this also has to be equal to, this is the same V as here, therefore this part has to be equal to this part, and you can invert it back over and you come up with the B frame components are the C matrix times the n frame components, essentially. Right? So that's this notation. Let's go back to the notation we're using in class a little bit. If we want to write a vector 2, 4, 6, and I want to express it in E-frame components. Tony, how do I do that? This right now is just a matrix. How do I make it represent a vector in E-frame components?
Multiply the...
Well, you could, but just notationally, what do I have to add? This is 2 times E1, 4 times E2. Yep, that's it, right? That's what we use. Easy. And let's say I want an answer in T. Just change things up. I'm curious, what are these, if I could write, what are the 3 vector components along the T1, 2, and 3 axes, right? So what this formula that I gave you showed is you can use the DCM, but using the 2-letter notation, which 2 letters do I have to throw here? T and E, right? So the TE matrix maps from, you're going from the E frame and you end up with the T frame, right? That's how we defined the C matrix. We went from N to B. We had N frame components and we ended up with B1, B2, B3. We went from the N vectrix and ended up with the B vectrix. It's all equivalent. Yes?
So suppose you had another mapping from E to B. So you had a DCM for EB.
Okay.
Can you go from T to B by just stacking those together?
Exactly. And we'll get to that very next. So let me just get to the slide and I'll show that then. But this is the basic definition. So I hope everybody here has used the DCM, rotation matrix, transformation matrix, whatever you used in your notation to map vector components from one frame onto another, and how to cascade them together. We'll get to that very next. But that's it. So with the 2-letter notation, if I have a vector expressed in E, I need the TE matrix to get that vector in T-frame components. If you ended up with a, let's say, BQ, and this is R in B frame, right? And you claim in a paper that's RQ, this should raise lots of warning bells. This doesn't make sense. What you'd have to do is transpose it, and if BQ transpose becomes QB. So with this 2-letter thing, you can look at, okay, this vector is given in this frame, this is given in that, this is mapped from here to here. All these letters should cascade and map up together, hopefully letting you keep track of it very, very simply. It means doing less errors. So that's vector coordinate transformations, which I know you've done. Now, let's go to addition, right? We talked about attitude descriptions not being a vector group. They're actually part of the SO3 group. You can't just take one DCM and add another DCM. Actually, let me go back and look at this. So the definition, if we have N and your B frame and pretend to have 2 right hands, okay? So if they're coincidental, exactly the same, what is the corresponding DCM description, Charles? If N and B are the same coordinate frame.
Tell me the ones are...
Right, because then this, if N1 is equal to B1, this is going to be cosine of 0, which is 1, and everything else is orthogonal to 0. You just end up with a diagonal matrix. So the zero rotation isn't just a 0, 0, 0, 0, 0, 0, 0, 0, 0. That wouldn't make sense because it's not orthogonal. You can't invert it. There aren't unit lengths. So the zero rotation is an identity matrix. That's what you have to remember, right? Good. So let's go back. Oh, actually, I was here. And so additions. Yep. Now we want to add several different rotations. I have 3 frames, the N frame, the B frame, and the R frame, both just given through the set, this vectoric sets of B123, R123, N123. So it's nice shorthand. So I'm just using not the 2-letter notation here, but just to see. So if C maps N to B, exactly what we had in the earlier slide, and the second line shows how B maps into R through C prime. So 3 prime in the 2-letter, this would be the RB matrix that goes from B to R. This would be the BN that goes from N to B. So if you cascade these together, you can say, well, if R hat is equal to C prime times B, I can take B and substitute it back in, and then just do that math, and you get, okay, C prime times C times N. And I'm looking for the mapping from N to R directly. Well, these 2 matrices multiplying together, I'm just calling that answer C double prime, is what maps N to R. If you do the 2-letter notation, to me that's actually easier, because then this was BN, this was BN, this was RB, and you get RB times BN, and you end up with RN. So the DCM allows a very simple way to add rotations. If I have the attitude from the inertial to the space station, this is the DCM, and then from the space station to the astronaut, this is the DCM, and you want to add the 2 orientations, you just multiply them out. If you did the identities, this is always the quick thing. If people would just add DCMs, so space station and inertial are the same, astronaut and inertial are the same. Therefore, BN and RB are all identity. If you just add it to identity matrices, you end up with 2s on the diagonal, which should give you huge warning flags and say, this, I can't be doing the right math, right? Because I'm not ending up with an orthogonal description. Yes, sir. What was the question?
That answered my question.
That answered your question. Okay. So good. So to add orientation, this is a very fundamental way. And if you know how to go from any attitude set to DCMs, even if you don't know how to do these Cayley-Klein parameters, addition properties, if you can at least map them to DCMs, you can add them here. And that's why the DCM is very important. We go as one of the reasons it's very important. So here we're doing additions. Let's say we want to do subtraction. So we're going to now say, look, you know Bn, and you know Rn, but I'm looking for the relative attitude of body relative to reference. So what I'm looking for is BR. How do I find this now? Go ahead.
Bn times Rn transpose.
Bn times, let's just make it in 2 steps. If I go Bn, you would need Nr, right? Because then you go from R to N, N to B, which gives you R to B directly. But we don't have Nr, we have the opposite. We have the inverse of it. And like with omegas, if you have the inverse of omega B relative to A, we just flip the sign. For DCMs, if you need the inverse of a DCM description, we just have to transpose or flip the 2 letters. So we can say this is equivalent to Bn Rn transpose. So you can see once you can do addition, you can actually also do subtraction. You just have to know, how do I get the, I'm not going from N to B, I need the one from B to N. Well, it's just the flipped, the transposed version of it. That's it. So then you can go back and forth and do addition and subtraction. This is a very fundamental way. There's no approximation in this. There's no small angle set. This gives you, to machine precision, always the correct answer. And so for many codes, you will see these things actually being used. But there are other ones that we use for particular coordinates, too, that are quite convenient. They sometimes exist, and sometimes it's just very complicated, and you go back to DCMs. Especially if you're mixing coordinates. If your sensing is done in quaternions, and your math is done in Rodriguez parameters, you need the difference between 2. I'm probably just mapping them to the DCM, doing it there, and then pulling out what I need. So you will see this process repeated a few times. Good. We're almost there with review of these things. Differential kinematic equation. This is really the one that relates, again, the omega vector to our coordinate rates. What we measure is angular velocity, the omega. What we use in dynamics is omega. But when we integrate, I have to somehow integrate the attitude. So here I'm using the DCM as an attitude description. So I have to come up with DCM rates. I have to have a 3x3 matrix which I can integrate and then find the new attitude, right? And how do we get that? So that's what we're looking for. Again, this DCM is just a 3x3 by choice. Nobody said we had to write those 9 numbers into a 3x3 form. We've chosen it because that 3x3 formulation is very convenient, it's orthogonal, has a lot of nice properties, it makes our life easier. But it's basically just 9 numbers we've stacked into a 3x3. This derivative doesn't have any frame dependencies. It's just cosine. Cosines are scalars. As we said earlier, the derivatives of scalars is just a time derivative of a scalar. That's not as seen by some frame, right? We talked about energy and mass in this case. Same thing here. So in homeworks, I can promise you there'll be problem 3.6. Many of you will be tempted. Oh, it's so, I want to put a letter here, but it's rubbish. Don't do it. Resist temptation. DCMs, you take in derivative, it's just a straight matrix derivative of these terms. That's what we're talking about here. So we have to relate it to omega. On omega, this is omega. If this is Bn, this would be omega Bn. And this is what we had earlier, the omega 1, 2, 3, and B frame components. This is what we have to map it together. Now, I'm going to show you this relationship here. This is one of your homeworks, I think. You have to prove this identity. So if I'm looking at individual vectors, the transport theorem holds. There's an I here. This vector is the ith component of a vectrix, which is really just Bi hat, in essence, right? And the inertial derivative of Bi hat is the same thing as the body frame derivative of Bi hat plus omega Bn cross that vector again. Classic transport theorem. And I can do that for every one of my vectrix components. And if you do that, you end up, there's a matrix equivalent thing of this that says the derivative of all 3 components can be written as minus omega tilde B hat. Now what is this omega tilde? In vector math here, if x crossed y is a cross product, one vector crossed another, there's a matrix equivalent operator, which is called the tilde operator. Sometimes called a cross product operator. Some people write it with a matrix with a little cross symbol sometimes. I always have it with the matrix with a tilde, that little squiggly mark on top of it. That times this. This you want to prove to yourself. Just take x as x1, 2, 3, y as y1, 2, 3. Do your classic way of doing cross product, look at the answer. Or take the x1, 2, 3, fill up this skew symmetric matrix times y1, 2, 3, and you should get exactly the same answer. The tilde matrix is skew symmetric, so you have 3 vector components and they fill the upper diagonal and lower diagonal part, but they have opposite signs. And this sign definition is heavily used, but not universally used. You will find some papers that flip the sign definition. Just look out for that. It really screws up other parts. But this is probably the most commonly used form. So check this out. R tilde, x tilde y, if you see that, you think it's nothing but x cross y. That's why if you have x tilde x, what would that have to be? Yeah. 0, exactly. A vector cross x tilde x, knowing that represents a vector crossed with a vector. If it's x and x, it has to be 0. And you can plug in the numbers and you see a bunch of x3 minus x, everything cancels out. Good. So go through this math, define this stuff, but you can see the inertial derivative of this. In the body frame, we know all these go to 0. Here, we don't just get omega cross the vectrix, we get minus omega cross the vectrix. So it looks almost like the transport theorem if we're working on a vectrix instead of vectors, as we have here. But there's a sign flip, and it comes out of the linear algebra. So once you plug in the vectors, B1, 2, 3, write things in components, you'll be able to prove this to yourself. This is basic linear algebra vector math. This is one of your homeworks. But given this definition, that's what we need to define the DCM rotation matrix. We'll get this, and then that'll be a good stopping point. So if we have B is equal to C times N, that's the vectrix, direction cosine times the vectrix. If I take time derivatives of this, on the left-hand side, this is a matrix of vectors. So here I do have to specify a frame. I'm taking an inertial derivative. That's going to be the inertial derivative of this set, because these components times a vectrix of vectors is still a vector, N frame. Then chain rule. The C varies with time, and the N might vary with time. In this case, no, as seen by the N frame, N1, 2, 3 are fixed. That's going to go to 0. But the C, and this is where I drop the N, because it's just a derivative of components. It's like in the homework when you have L times A2, right? The derivative of L is just a derivative of a scalar. Either it varies with time or it doesn't. And here it does. So we keep that. This part drops out. That gives you c dot times n hat. That's just from the basic definition and chain rule. The next thing is, too, we also, earlier, this is what you do in your homework, the inertial derivative of the b vectrix is minus omega tilde b. If this has to be the same, we can plug in this definition, drop it in there, and if we do that, then you have minus omega tilde c n hat. This all comes together. This has to be equal to the same derivative here, so this gets pulled down. So if this times n hat is equal to this times n hat, you can group that together. And then this bracketed term times n hat has to go to 0. This is the classic math argument. This has to be true for any set of n hats. You can't pick a particular frame which happens to make this math go to 0. This has to be true for any frame. So the only way that happens is this bracketed term has to individually go to 0. And voila, we have derived the differential kinematic equation that you need to integrate. So c dot is equal to minus omega tilde c. Or if you want to write this out in the two-letter notation, I'll do that. That would be bn dot ends up being minus bn tilde times bm. Now this b vector, when you take vector components and construct this tilde matrix, with respect to what frame do we have to take vector components? It's a subtle detail. If you go look at that, if you go back, look at the definition we had here when we created this stuff, and when you derive this stuff, actually, you will always pick omega bn to be expressed in b1, 2, and 3. So this differential kinematic equation, you can make a note, this, if you have bn dot, then minus bn tilde, bn has to be expressed in b-frame components. Otherwise, things are flipped. Again, it seems trivial now. Wait till you have 6 frames and everything gets relative. This is where you really want to be on top of these details and make sure you get the right stuff. Louis.
If you expressed your omega in the inertial frame, would you right-hand multiply instead of left-hand?
There's ways to flip and come up with equivalent definitions, yes. If you use this definition, that's what's required. There's ways to rewrite this where you could have other components and kind of build that in. Yep. So once you know the basic tools, there's lots of combinations on how you could rewrite this into terms of other stuff and come up with an analytic answer. But good, so we're just 2 minutes over, so we'll stop here. We'll pick up with a brief review of DCMs, and then we're going to go into the next set of attitude coordinates. Things will get more involved.